Hello, my name is Danielle Gloyston, and I will be presenting on the synthesis of ketamine today. So for a little background, ketamine's history really starts with phencyclidine, which is also known as PCP. PCP was synthesized in 1956 by Parke-Davis Company, and they noticed that it had great anesthetic properties, but also created a really intense prolonged emergence delirium, which is delirium associated with when you're coming out of sedation. So because of this, they thought it was undesirable for human use and went back and started looking into making shorter acting derivatives. In 1962, Calvin Stevens, an organic chemist at Parke-Davis, created ketamine, and as an analog of PCP. Just for reference, PCP is going to have a 6-membered ring here. It won't have this and it won't have this, but the core is definitely the same. And then from 1964 to 1966, they studied it on humans, and in 66 published a paper. Ketamine was able to rapidly produce analgesia as well as anesthesia, and that would be under a minute, lasting for 30 minutes, and it was very easy to redose. It was also safe to redose. And most importantly, it had a very short-lasting delirium upon coming out of the sedation, as compared to PCP. So in 1970, Ketalar, which is an S and R chiral mixture of the two enantiomers of ketamine, was approved as an anesthetic. Since then, ketamine has appreciated expanded clinical relevance. It is used in both animals and humans as an anesthetic. It is also used in acute and chronic pain management, and it is very recently used as an antidepressant. This is called Spravato, and it was FDA approved in 2019 as an intranasal spray, and it is just the S isomer. And of course, it is used recreationally because of its dissociative effects, and it is in the dissociative drug class. It is also known recreationally as Special K or just K. So here is a little summary of some of the clinical uses of ketamine. You can see it's used in pediatric patients, as well as the elderly, and in emergency department people where they don't know the medical history. And this is because, one, it has, for pediatric patients, it's 93% bioavailable intramuscularly compared to 100% bioavailable intravenously. So it's still very bioavailable. You don't have to fiddle with the vein. Also makes it useful in battlefield mass casualty situations. It is also helpful and especially useful in these sort of population subsets because it does not depress respiration as opposed to other anesthetics. And you can also see that it has a wide variety of uses for pain management. And then also here's the psychiatry and neuroscience section with depression, suicidal ideation, and PTSD. And finally, it was used in modeling schizophrenia for a while until they realized that, just because something can give you the same set of symptoms doesn't necessarily mean it has the same mode of action. So, chemical properties and psychoactive effects. Ketamine is a white powder, but it is clear in solution. And in terms of solubility, it is soluble in both water and lipids, and that's because of these nonpolar regions as well as polar regions. So it has a wide therapeutic range, and death by overdose is rare and mostly just associated with, because it acts on the central nervous system, using it with other things that depress the central nervous system, like alcohol or benzos or opioids, can be fatal. But if you're using it therapeutically, it's very safe. And in terms of psychoactive effects, that's also very dose dependent. Low doses will provide stimulant effects, but they'll be pretty mild, and you might experience a little bit of distortion of time and space, as well as an increased sense of well-being. But high doses, on the other hand, can make people completely dissociate from reality. And this is also coupled with full body numbness and loss of control over your body as the anesthetic property really kicks in. So in the recreational drug world, this is called K-holing, and it can be very uncomfortable for people who don't end up liking that dissociative experience because your body has been anesthetized and you can't communicate your discomfort and ask for help at all. So it can provoke a lot of anxiety. Another note on its recreational use is that it's used as a date rape drug because of its anesthetic effect. So ketamine's primary mode of action is as a non-competitive antagonist of the N-methyl D-aspartate receptors. Non-competitive means that it doesn't bind to the neurotransmitter receptor site itself, but rather allosterically and in the ion channel. So it's actually binding in two places. It has an open channel block mechanism, which requires glutamate to bind to the receptor and open the channel, where ketamine then comes in, binds deep within the channel, and prevents the flow of ions. And this therefore prevents the electrical response. And then, of course, in turn, the lack of electrical response translates to what impedes the brain's sensory connection to the body. So the S isomer has been found to have a higher affinity for the NMDA receptor site, and this produces 3 to 4 times greater anesthetic effects, but also a more rapid recovery of psychomotor skills and decreased incidence of emergence delirium. Other research talked about how maybe the R isomer is more effective as an antidepressant, but the Spravato spray, intranasal spray, is the S isomer, so I'm not really sure if that's just because in general the S isomer has greater binding, so it's just stronger, or maybe that research ended up being inconclusive about the R isomer. Overall, though, the anesthetic, analgesic, and antidepressant effects are largely tied to the NMDA receptor, but ketamine and its metabolites also act on a wide variety of other targets, and I will show those in the next slide here. So as you can see at the top, NMDA is acting on, or is that antagonism is going to create all three, as well as the antidepressant effects. But there's also been research investigating whether agonism by a metabolite called hydroxynorketamine, antagonism of the AMPA receptors, is maybe what's also causing the rapid antidepressant effects. Overall, though, you can see that there are a ton of different places that ketamine and its metabolites are acting in the body. So moving on to the synthesis, I chose the original patented synthesis by Stevens. He uses no stereochemical control, and he produces both isomers. So it's got 4 main steps. First is this Grignard, which we all know, and subsequent hydrolysis to make the ketone. And then we have an alpha bromination right here using bromine, followed by an immination reaction, which is going to kick off water, and that water is then going to come in and act as a nucleophile after bromine jumps off in an SN1 reaction. So then this is heated, and we are going to get our final product. I will refer to these side notes throughout the more detailed look on all of these steps. So jumping right into the Grignard reaction, which we all know pretty well. These are 2 very readily accessible starting materials, and in this reaction, cyclopentane, this carbon here is going to act as a carbanion and attack the carbon of the nitrile group, kicking those electrons back up onto nitrogen. Nitrogen is then going to grab 2 protons in solution during the acidic hydrolysis step workup. From there, water in solution is going to nucleophilically attack this carbon here and push those electrons back up onto the nitrogen, where we get our tetrahedral intermediate here. We're going to get a little proton transfer, and eventually you can see here their oxygen is going to kick its electrons back down and form this ketone. So from here we are ready to move on to the next step. This is the alpha bromination step. It can also be done in other reports and other published papers. I saw it done with NBS, which is N-bromosuccinimide, and that's going to proceed via a radical pathway. That radical pathway would be putting a radical first here, which would be stabilized by this ketone right here. But for the sake of sticking to the patented original synthesis that I looked at, I will be just using bromine. So this then therefore proceeds very simply through an initial keto-enol tautomization, which just happens, and then the collapse back down is going to create an SN2 attack from this carbon to this bromine here, kicking off the other bromine and creating our next product. This product is unstable because of this bromine here on a tertiary carbon next to a carbonyl, and therefore needs to be used pretty immediately after. So for our immination step, it's going to involve methylamine, which is this guy right here. And because we know methylamine is a controlled substance, this synthesis is pretty hard to do illicitly. So therefore ketamine is generally illicitly sourced by the diversion of prescription products, rather than being made in secret laboratories like in Breaking Bad. Okay, so for this, we have seen this before. We generally know how this works as well. The primary amine is going to have a nucleophilic attack on that carbon of the carbonyl, pushing those electrons up onto oxygen. There's going to be a little intramolecular proton shift. This can also be done with an acid catalyst, but nothing too acidic, because our methylamine can also grab another proton from solution, and in which case it would no longer be a very good nucleophile. But the Stevens patented design synthesis does not have acid used as a catalyst, so I just proceeded to do intramolecular exchanges of proton. So for this next step here, I show bromine kicking off. This can really happen at some point later in the synthesis, or this next step could proceed with water being kicked off, just completely gone with bromine still attached to here. But for the sake of just kind of making everything look pretty and streamlined together, and because it quite possibly could happen, I show bromine kicking off for the start of this SN1 reaction at this carbonyl, at this carbon center. Tertiary carbocation is then formed, just like in an SN1 reaction, which it is. And so then when nitrogen kicks down its electron pair to try to form a double bond, and this hydroxyl group would be normally kicked off, it instead just shifts directly over to this cation and has a nucleophilic attack on this tertiary carbocation. So that's why I do this way, but there could be other proton shifts. Maybe a water molecule comes in, this guy completely goes off, and this guy goes in here. But why not do things intramolecularly is how I saw that. Okay, moving on. The next step is just the proton is removed from that protonated imine to form our imine. And from here, we are ready to go on to the ring expanding rearrangement. So this one's pretty cool. I was not able to find this exact reaction mechanism discussed explicitly online through my research. By that I mean that in Stephen's paper and in his patent, he never discusses a mechanism, and in anything that talks about the making the synthesis of ketamine, I couldn't find anyone doing any arrow pushing on this or referencing any sort of mechanism that I can look up elsewhere. So just through doing substructure searches, I found that the most likely thing that's happening here is an alpha ketal rearrangement, and this one just happens to be ring expanding rather than just like a methyl shift or something of that variety. So without further ado, I'll jump in. Just another note, in that big general outline, I showed that an acid can also be used to catalyze this, and that has been shown to reduce the time it takes to do this, but for the sake of sticking to that original patent, I proposed a mechanism here without using any other source of protons. Okay, so intramolecularly, I'm going to show that this lone pair on nitrogen goes and grabs a proton. It's going to grab this proton that's right next to it just because of basic proximity. That is going to kick these electrons onto oxygen, which are just going to kick right down to try to create a double bond there. And because this carbon 2, is attached to 1, 2, 3 other carbon centers, it's going to have to break a bond with one of these carbon centers. It's definitely not going to break this one because it's the strongest. And in terms of the 2,6 versus 2,3 bond, it doesn't really matter because there's no other substituents on this ring. So for the sake of my numbering system, I'm just going to show that the new bond is being formed between 6 and 1. So this bond is going to break, forcing the electrons just very temporarily onto carbon 6. This is going to happen so quick that the carbanion is going to nucleophilic attack on the carbon 1, which should have a partial positive charge based on the fact that this nitrogen has just grabbed this other proton right here. So generally a buildup of positive charge is going to make this happen in conjunction with the fact that this does not want to be a carbanion. Very quickly is going to just shift right over and form a new bond with carbon 1 after breaking this one. And from there, these electrons are going to shift back up onto nitrogen. So as you can see in our product, this is ketamine. We have all of our numbered carbons that are of use in this. 1 and 6 has formed a new bond, shown here and here. And 2 and 6, that bond was broken. Our alcohol originally has now been oxidized into a ketone at carbon 2, and our imine was reduced into a secondary amine. And so that's our final structure. And that is what I thought probably most likely happened. So just as a alternative set of reactions here, I just wanted to show you that in making S-ketamine, which is what's used in the Spravato nasal spray, which is the S-isomer of ketamine, they used a ruthenium-based chiral catalyst in something called the Noyori asymmetric transfer hydrogenation reaction, and that's where they introduced the chirality into this molecule. The whole design you can see is completely separate, but I'll just point out that they introduced, this chiral catalyst introduced a asymmetric center right there, which is then transferred all the way over here in this reaction from this carbon to the carbon that we want it to be on over here. And that's where it's seen in the final product. So that's just a separate way to make a more asymmetric synthesis. And they are claiming to have 97.7% enantiomeric excess with pretty high yields throughout as well. Oh, no yield there. Okay. Cool. So my references are on this page here. And thank you for listening.